with climate change and archaeology being central to my PhD. It's a topic that I find really fascinating and really passionate about, so I hope you find this talk interesting and enjoyable. So, as this is my first talk here, and one of my first talks since completing my PhD, I thought I'd do a wee bit of background on myself. So I studied environmental science, first of all, at the University of Stirling, and sort of throughout my undergraduate degree became interested in archaeology, and particularly the application of geoarchaeology, which essentially uses principles and methodologies from environmental and earth sciences to better understand the history and formation of archaeological sites. I was fortunate enough to conduct this type of research, work in the UNESCO World Heritage Site of Kathmandu, where basically the 2015 earthquake destroyed a lot of significant monuments in the Kathmandu Valley. And as geoarchaeologists, we were able to access the soils and sediments beneath them and gain insight into the early history of the sites. So that type of research kind of underpins why I wanted to go on and do a PhD. So quite a swift transition from undergraduate dissertation on collapsed monuments in Nepal to a PhD on Iron Age structures in Scotland. My PhD focused on the effects of climate change on sandstone heritage in Scotland through the application of geoarchaeology techniques. So when you think of impact of climate change on archaeology and heritage, quite often it's these really vast impacts like sea level rise engulfing sites and storm events severely damaging sites. But my research focuses on something that's almost sort of unrecognized. It kind of operates in the background. It's the small scale impacts, and that's the chemical, physical, and biological weathering of stone material within archaeological sites and historic monuments. So these processes by nature are a lot slower than your storm events, but over time, especially in a climate change future, these processes are likely to be severely limiting factors in a site's longevity. So I successfully defended my thesis just last month, so I'm now looking to sort of pursue my career in heritage science. So it's a great opportunity to talk with you all this evening. So that's enough about me. Tonight's talk, I'll just run through a wee bit of the structure. So first of all, I'll talk about climate change on a global scale, what it actually entails, a bit of the science behind it. And I hope it will be useful for sort of experts, non-experts alike. It'll be quite a broad talk. I'll go on to talk about climate change in Scotland. I don't know why that slide has skipped onwards. Yeah, I'm going to talk about climate change in Scotland before starting to make mention to some of my research that integrates climate data with archaeology, and then some of the techniques of conserving at-risk archaeology, and then a particular case study from Upper Glendevon Reservoir, which is climate change unveiling unseen archaeology, and then we'll have time for a wee chat at the end. Probably about 45 minutes talking. So this section will touch firstly on the general science behind climate change, what's happening on a global scale. Unfortunately, you can't talk about climate change without talking about CO2 emissions. And these graphs are readily available from the Mauna Loa Observatory in Hawaii and constitute the longest record of direct measurements of CO2 in the atmosphere. Data is obtained at an altitude of 3,500 meters in the northern subtropics. And the graphs show mean monthly carbon dioxide in the atmosphere in parts per million. Red lines and symbols represent the monthly mean values, centered in the middle of each month. And the black lines and symbols represent the same after correction for the average seasonal cycle. So these provide an excellent sort of visual representation of just what underpins climate change. We have the seasonal cycling, which is the same year on year, where we have more CO2 in the atmosphere in the winter and less in the summer. But as you can see, the cycles are the same, but it's amplified year on year. So much so that since the 60s compared to now, we have about 100 parts per million increase in CO2 in the atmosphere. So these graphs are from the Mauna Loa Observatory itself. but it's the same on a global scale, and these are the global trends averaged over marine surfaces, and they show an irrefutable increase in a global output of CO2, primarily as a result of anthropogenic sources such as the burning of fossil fuels. So how does this tie in with the climate change that we observe? Well, with rising CO2 levels come rising global temperatures, and this is a great resource from the University of Reading. It's a really simple visual representation of change in temperature measured in each country for approximately the last 100 years. The timescales vary country to country, but the global trend, which is observed in each individual country as well as globally, is that the stripes turn from mainly blue to mainly red in more recent years, illustrating the average rise in global temperatures. It can be visualized in graph format as well, and as you can see, as you move towards sort of 2000s and onwards, temperature increases are refutable, about a 1.2 degree increase globally. So looking a wee bit at the IPCC, that's the Intergovernmental Panel on Climate Change, and their special report in 2018 on warming of 1.5 degrees. So from the figure, you see the temperature here at 2017, just at the time, just before they released their special report. So CO2 emissions determine the probability of limiting warming to 1.5 degrees, which is the global target at the moment. So each line that leads on into the future is intrinsically related to CO2 emissions. So put simply, reducing emissions quickly and rapidly will keep temperatures roughly where they are. You can see that on the bottom range of this figure, if we rapidly reduce CO2 emissions. Conversely, as we're going at the moment, if there's a continued rapid increase in CO2 emissions, we'll head up towards 1.52 degrees of warming. So looking at the figure, you can see sort of about 2040 to 2060 is a real tipping point. So right now in 2021, we really are on the edge right now, and the decisions that we make at the moment, such as at COP26, will have a massive implication on future temperature rise. Each of these CO2 emission scenarios, those are the lines leading off the previous figure, are incorporated within IPCC reports and the United Kingdom climate projections. They're referred to as representative concentration pathways, or RCPs, and they're used to predict warming based on CO2 emission trajectories. So you have 4 emission scenarios at the moment. RCP 2.6 being a very stringent pathway, according to the IPCC. It requires that CO2 emissions start declining by 2020. So we've effectively already missed that by a year, and go to net zero, go to zero rather by 2100. RCP 4.5 is described as an intermediate scenario where emissions peak around 2040 and then decline. RCP 6, the emissions peak around 2080 and then begin to decline. And RCP 8.5, the worst case scenario, emissions continue to rise through the 21st century. So again, 2040 to 2060 really appears to be the tipping point, after which the scenarios diverge quite markedly. And it's important to note that we are heading towards the worst case scenario, but it's important to note that this is the worst case scenario in terms of the IPCC reports. This is their worst modeled prediction. It could feasibly be worse. It's not to say that RCP 8.5 is as bad as it possibly could be. There is a chance that we could be even worse if we don't make immediate changes, and that's why things like COP26, with all the world leaders meeting, is so important that meaningful change actually has to happen, or it'll go out of control. So, as I've mentioned, the rise in CO2 is directly linked with human activity, anthropogenic activity producing greenhouse gases. So although a warming of 1 degree, it doesn't sound like much, but human impact on the planet has actually been so pronounced that it called into question the delineation of recent geological time. So the figure on the left shows recent geological time, when there's growing literature to suggest that we've in fact moved out of the Holocene, which is the most recent epoch in the Quaternary period, commenced about 11,700 calendar years before present, and actually transitioned into the Anthropocene. It's an unofficial unit of geological time. It's used to describe the most recent period in Earth's history when human activity started to have a significant impact on Earth's climate and ecosystems. Informal acknowledgement of this transition into the Anthropocene rests on whether human activity has become sufficiently recognizable enough to leave distinct stratigraphic markers in sediments and in ice that's significantly different from the Holocene. So there's various proposals for delineating the base of the Anthropocene when it commenced. There's an early Anthropocene aligning with the advancement of agriculture and deforestation. There's an industrial revolution which occurred around 1800 as that for the base of the Anthropocene, and the Great Acceleration taking place during the mid-20th century, characterized by rapid population growth and industrialization. The Industrial Revolution is actually it's most favored in the literature as when human impact became sufficient enough to actually put us into a new epoch. But the reason I bring that up is because that regardless of a formal definition of or acceptance that we are actually in the Anthropocene as a new epoch, the very notion of it, that actually human impact on Earth has actually caused us to question geological time, gives a sense of actually, what we're doing to this planet and what we are going to be exposed to in a climate change future. So I mentioned IPCC a few times so far. I'm sure many of you are aware of their reports that come out. There's one that just is in the process of coming out. They released some material in the last couple of months, but they're really comprehensive documents, thousands of pages long, about knowledge on climate change, causes, impacts, and response options. They're readily available to download online. They publish special reports as well. The 2018 one was particularly it gained some news coverage about their warming of 1.5 degrees. But the severity of climate change and the sort of threats that they warn us of increase year on year. So I went through some of the reports since the 1990s, just to have a look, just about archaeology and heritage. So they typically release a scientific assessment, the basis for the report, the impacts, adaptations, and vulnerability, potential mitigations, and a synthesis report. So it's not just the sort of synthesis report that gets shouted about at the end. There's actually an awful lot goes into this. So yeah, I went through it and first of all had a look for archaeology, and there was no mention. So change tactic, and I had a look for heritage within it. So you can see over time there's no real correlation with, as we know more about climate change, heritage becomes, or archaeology becomes more talked about. There's no greater mention about it. And where it is mentioned, it tends to be in the impacts, adaptations, and vulnerability documents, as you can see from some of the peaks in 1990, 2001, 2007, and 2013. But crucially, the mentions of heritage are actually extremely vague. They say things like climate change may require a greater effort to protect cultural heritage, but we know that it will, and this is a problem, that these documents from the IPCC are, they're spread all throughout the world, the government agencies, and I may be biased, but heritage is definitely underrepresented as one of the most important resources that we have. And it's been talked about since the 1990s as well. You can see in the 1990s there was almost 20 mentions of heritage, but it's not until relatively recently that climate change impacts on archaeology and heritage have really been studied more extensively. So that brings me on to the next stage of my talk, which is beginning to look more closely at climate change, specifically in Scotland. So I've mentioned CO2 and temperature, but it's important to note that climate change brings about more than just a temperature rise that impacts archaeology sites and heritage sites. So shown on screen, this is sort of 2018 data from Historic Environment Scotland and a risk assessment. So we see fewer days of frost, fewer days of snow cover. That means less prevalence of processes such as freeze-thaw in historic monuments, but when it does happen, exerts a greater force on building stone. We have a longer growing season, quite markedly longer, 33-day long growing season, which promotes biological activity, of course, on our monuments. You can see walking through not just archaeology sites, but through towns and cities, Stirling, Glasgow, and Edinburgh, you can see biological activity in stone monuments and stone structures. Rise in temperature of around 1 degrees, again, impacts microclimates within archaeology sites and heritage sites. Increased rainfall has a whole host of impacts on sites, including just the physical action of the rainfall, but also sort of chemical weathering as well, penetrating into stonework. And of course, there's sea level rise, which really puts at risk our coastal heritage. So refer back quickly to show your stripes, this time for Scotland. And if you think back to the global trend, Scotland follows this. There's clear warming, particularly from the 1990s onward. But this is a very simplistic diagram. We have more complex, higher resolution data available in the UK that we can apply to archaeology and heritage science. So the data comes from the United Kingdom Climate Projections, or UKCP for short. So they brought out a database of climate projections in 2009, providing projections across the UK for variables such as temperature and humidity, related to low, medium, and high emission scenarios, essentially the same as these concentration pathways that I mentioned a few slides ago. The low basically being a severe reduction in CO2, high being a continued increase. So under a high emission scenario, for example, from the 2009 database, by the 2050s, Scotland will experience a sea level rise of 16.5 to 28 centimetres, rise in temperature of 2.8 degrees in the summer and 2.2 in the winter, and a precipitation reduction of 13% in the summer and an increase of 16% in the winter. So it feeds into this narrative that Scotland generally will experience warmer, wetter winters and warmer, drier summers. It's related now to heritage. The data was integrated within Historic Environment Scotland's pioneering risk assessment, which they used to model climate change impacts on their properties and care. So alarmingly, they found that 89% of 352 analysed sites are at high or very high risk associated with climate change, which paints a pretty bleak picture for the future of some of Scotland's most treasured sites. Recently, the projection database has been updated to UKCP 18. It brings about a more robust package, because actually from 2009 to 2018, our climate changed again. So the average temperature over the most recent decade, which was 2009 to 2018, has been on average 0.3 degrees warmer than the 1981 to 2010 average, and 0.9 degrees warmer than the 1961 to 1990 average. And all the top 10 warmest years for the UK in the series from 1884 have occurred since 2002. The average hottest day of the year has got warmer, and the most recent decade has been on average 1% wetter than 1981 to 2010 and 5% wetter than 1961 to 1990 for the UK. So a wider range of data is now available from 2018, but again, it feeds into this narrative once more that we're going to experience warmer, wetter winters and warmer, drier summers in a climate change future. So somewhere like Kilmartin on the west coast of Scotland already experiences high levels of precipitation. It'll become even wetter, particularly in the winter. So what sort of consequences will you see? The sort of flooding of sites and the chemical interaction of rainwater with stone monuments. So crucially, to heritage scientists and archaeologists, how can this data be used in archaeology and heritage science to understand future impacts of climate change at important sites? And that leads me on to some of my PhD research. So the overarching question of my PhD was, what impact will climate change have on the weathering of sandstones that are incorporated in archaeological and heritage structures? So it was quite daunting actually coming into this as just out of my undergrad, but apologies, I keep jumping forward. So I had to develop an innovative research design to begin with, one that integrated weathering processes with the built environment and climate projection data to try and build up an evidence-based decay model specific to different sandstone types. As other studies in the wider literature tend to focus on pristine, relatively recently quarried sandstone, but I find that crucial relatability to the built environment is lost when you do this. So culturally significant sandstone has a memory effect embedded within it. So decades, centuries, or millennia of above ground exposure leave an observable mark in the stone, which sets it apart from pristine materials. So for me to gain insight into climate change impact on heritage sites, I have to access culturally significant stone that's been exposed in a monument, so that we can understand how climate change will impact already weathered stone. So in an effort to fill this literature gap, I was led to broch structures. And today I'm going to mention a wee bit about our work at Borwick Broch and very briefly Clachtall Broch, but I promise this won't escalate into a talk on brochs as much as Kenneth would maybe enjoy it, but I'll try and keep it short on the broch side of things. So Borwick Broch was described in the late 19th century by Watt as a broch situated on an 80 to 90 foot promontory. It took the appearance of a grassy mound on the western mainland of Orkney. Without getting into geology too much, it is built with lower Stromness flagstone. It's a middle old red sandstone deposited just under 400 million years ago. They're characterized as being abundant in dark, silty mudstone, interbedded with siltstone and fine sandstone. They have a high pyrite and dolomite content, so it tends to turn a yellow-red colour on weathering. Borwick was one of my chosen sites due to its particular cultural significance and the fact that it's been the subject of archaeological investigation. So meaning for me, there's an abundance of culturally significant sandstone lying right next to the broch in the form of archaeological spoil that I can get my hands on to analyse that type of material. So I know that it's been exposed for about 2,000 years in a broch. So the big question is, how would it proceed to weather in a climate change future? So sandstone samples were taken from archaeological spoil associated with the broch as weathered stone. As well, to serve as a baseline, the pristine samples of the same sandstone type were taken from geology outcrops nearby. So I mentioned at the start of my talk that I use geoarchaeology methods. Samples were analysed using a lot of different techniques, but today I'll focus on thin section and scanning electron microscope mapping. They're really common in geoarchaeology and in stone weathering research, and they basically allow microscopic insight into sandstone structure, chemical composition, and weathering features. So for those not familiar with the techniques, the image on the top left is a thin section slide of a piece of Stromness flagstone from Borwick Broch. Essentially, you mount the sandstone onto a glass slide and grind it down until the stone has a thickness of about 30 microns, so about the thickness of a human hair, meaning that when you put it under a microscope, light can pass through, and you get images such as in the bottom left of the screen, where you can actually pick out features within the stone. Over on the right-hand side, you've got the scan electron microscope, or SEM. Again, you place a sample in the SEM and analyse the chemistry of samples. Different elements show up as different colours. So I was interested in this sandstone life cycle from geological deposition to use as a building material where it's exposed to climatic conditions, and then into the future where the material will be exposed to climate change. So each stage of this life cycle has an observable impact on the stone. And the first stage of the life cycle is from geology to broch. It's really important to understand this transition because that's what underpins the weaknesses in the stone. You get an idea of how it will weather. So in order to do that, we have the geoarchaeology techniques. So the lower Stromness flagstone contains a number of significant vulnerabilities, and these are shown on the slide. So the figure on the left is a scan electron microscope map that picks out individual elements and shows them in a specific colour. So for example, the top left in the orange colour represents quartz, the dominant constituent of any sandstone. You have aluminium on the top right, and this is feldspar, again a key component of sandstone. And in the bottom two, you have on the left, you have magnesium, which is in purple, and you have calcium in yellow. So these are the main constituents of dolomite, which is the primary cementing agent in the stone. So if you imagine you have quartz and you have feldspar, what holds them together is this dolomite cement. So you can see in these maps at the bottom, at the surface of the sandstone, there is very little dolomite. It is being lost through weathering, and it causes a red crust to form around the sandstone, which you can see on the slide in the middle. And the crust of a sandstone will behave differently to the interior of the sandstone. So it's an area of weakness where the material could be lost. Additionally, you can see these dark colored nodules. These are pyrite nodules. So these are composed of primarily sulfur, which is highly reactive. And when it reacts with water, it forms sulfuric acid, which dissolves magnesium and calcium around the nodule. Again, a weakness in the sandstone, the actual dissolution of the cement that holds the stone constituents together. And on the right-hand side, very simply, you have a crack, but you can see under the microscope the type of sandstone that it is. It's full of micro cracks. So, with knowledge of the material's weaknesses and the effect of exposure since the Iron Age, I began thinking about the material becoming climate sensitized, exposed to more extreme climatic conditions in decades to come. So to understand that impact, I developed a series of climate change experiments based on the available climate data that I ran through earlier in this talk. So at the University of Stirling, we have a controlled environment facility, or CEF for short. So samples can be placed in these climate chambers and be exposed to highly specific temperature, humidity, and precipitation fluctuations, which effectively allows me to expose samples to climate change in a simulated manner and analyze their response. So that's a really good analytical tool to have to understand building material responses. So I'll discuss one of the experiments that I undertook, and it was very much informed from the climate change risk assessment that I mentioned at the beginning of the talk. And I ran an experiment called a climate change year. So samples were exposed to temperature, humidity, and precipitation parameters anticipated in 2055. Again, I mentioned that 2040 to 2060 is this tipping point where if we go down the concentration pathway of 8.5, the effects are going to be pronounced. So that led me to use that pathway for my analysis. So I gathered data from the Climate Projections 2018, which I've discussed at length earlier. So that gave my research relatability to real climate data. So there's a lot of research out there that uses these types of chambers, but it exposes samples to unrealistic conditions. It freezes them and then it ramps the heat up to 30, 40 plus degrees. But in Scotland, even in a climate change future, they're not going to be exposed to those sorts of extremes. It's about exposing them to what they will actually be exposed to try and understand what will happen to the material and then the sorts of conservation plans that can be put in place as a result. So samples were exposed for about 12 weeks, with each week representing a month of real-time exposure. So temperature, for example, fluctuated from the daily minimum to the daily maximum temperature. Humidity remained constant for each week, and rainfall was sprayed on samples based on typical days of rain per month obtained from Met Office data. So, for example, in the top left, in January, The temperature went from around 2 degrees up towards 6, 7 degrees. The humidity remained at 86%, and about just under 40 millimeters of rainfall fell on the samples on 5 of the 7 days of the week. In January, there's typically about 21 days of rainfall, roughly about 5 and 7 days. So that gives me the climate change response. But in order to have a control for it, I had to run a control chamber, which would expose the same types of samples to 2018 conditions, so that I can disentangle the effects of climate change from the effects that would happen if there was no change in climate from 2018. So it's important to note that from these experiments, you're not anticipating dramatic results where the sandstones crumble and turn to dust. It's about getting realistic data to understand how different sandstone types will react to climate change. So these are the responses from the naked eye. Sample failures shown on the left-hand side. This was actually quite unexpected, that even along these pre-existing microcracks, you've actually got failure of samples. This would be visualized as like a surface regress in a broch structure. On the right-hand side, you have salt formation. You might be wondering what salt has got to do with climate change, but if we're talking about wetter winters, salt penetrates into pore space in sandstones. When it crystallizes, it expands and exerts pressure on the pore space on either side. So if it's wetter for longer, it doesn't crystallize as frequently. But when it does eventually dry and get the chance to crystallize, it's a lot more dramatic. It exerts a much greater force on the stone material around it, again weakening the sample. So we also saw, I mentioned the dissolution of dolomite, the cementing agent in the stone. On this image on the left-hand side is a demonstration of that occurring. So you've got a loss of the material that binds the stone together, and you get what's called secondary porosity. So it's not the porosity that's within the sample when it's deposited. It's occurred through experimental work and through being exposed in a culturally significant monument. As well, on the right-hand side, we saw aggressive weathering of sulfide nodules. So the top right is a carbon map. So essentially all the areas in red are carbon, areas where there is no sandstone. It's the glass slide that's coming through. So you can see that this is the nodule here, and it's aggressively weathered, and the porosity surrounding that sulfide nodule has increased. So these are actually quite dramatic responses from quite a short length of exposure in an experimental way. But it's important to put it into a wee bit of context. So I won't talk about this sandstone much, but this is from Clachtol Broch. So the exact same experiment happened to these samples. This is Torridonian sandstone. It's far more robust than Stromness flagstone, and the response is very different. So in before and after images in the top left, you can just see some minor surface losses. Under the microscope, this is what it looks like. You have distinct areas where grains have become weakened, and you've got granular loss at the surface of the stone, which in somewhere like Clachtol Broch would be visualized again by the stone surface regressing within the broch. Again, on the map on the right-hand side, you have quartz at the top and you have carbon at the bottom. Carbon, again, being the pore space, where grains have been lost and it is now porosity. Additionally, it has distinct clay layers within it, visualized in this image in the top left here, and you get material loss around them. You also get the occurrence of vertical cracks coming into the stone from the surface. So if you basically follow the black line in the top left map, there's a crack coming from the surface of the sandstone. So from this experiment and others that I conducted that I don't quite have time to go into, I was able to generate decay models that are specific to different sandstone types in a climate change future, effectively informing us and Historic Environment Scotland how sandstones within historic structures and archaeological sites, how they will actually respond to this climate changed future, which is really important for an organisation such as them. So although this is just on a couple of sandstone types, it's a sort of methodological design that can be applied to lots of different sites. And it demonstrates that although the materials have been exposed to the exact same parameters, sample response is very different based on the sandstone type. So it's not enough to say, this is how archaeological sites will weather in a climate change future. You can't do it. It's got to be specific to the building material and the site itself, which is where important research such as this comes in. So, for example, you would expect relatively soon for a lot of the stone in Borwick Broch to fail in a climate change future. And in 30, 50, 100 years down the line, the sandstone types are at really severe risk of extensive degradation. Conversely, at Clachtall, you've got a bit more time. So it's about prioritising sites that are maybe at greater risk on climate change than others. So that's a wee bit about my research. But at the University of Stirling, I'm part of an excellent research group where climate change plays an important role in understanding the longevity of archaeological sites and wider heritage sites in a climate change future. So we have myself, obviously, we have Hazel Blake that's looking at digital landscape applications in managing precipitation change in heritage sites. We have Tim Meek that's looking at harling and finishing as traditional solutions to heritage building stone protection. And we've got Gavin Douglas looking at excavating for a climate change future. So our research feeds into wider conservation planning, while testing new and innovative research designs aimed at understanding the effects of climate change on archaeology and heritage sites while there's still time to act upon our findings. So what can be done to protect heritage sites? Well, in the wider literature, work by Historic Environment Scotland, climate team and the science team is really at the forefront of climate change impacts on heritage sites, monitoring sites and understanding how they'll be impacted by climate change and how we can prevent the most profound effects. David Harkin et al. Produced this adaptive intervention hierarchy, aimed particularly at coastal sites, but has relevance to all sites, ranging from general maintenance and managed loss, all the way through, from general maintenance to managed loss with various steps along the way. Examples of these, I'm sure many of you are familiar with, things like the Hill House in Helensburgh. So to protect the house, they embarked on a very ambitious conservation program to actually cover it from the elements. The walls were suffering from moisture, so to protect it from the rain, they built a superstructure around it. And the National Trust actually see that this is arguably as pioneering as building the Hill House in the first place. Another very famous one, Scarborough. It's right on the coast, on the western mainland of Orkney. It's a particularly weak coastline at that particular section, and the site is at risk of loss due to climate change with sea level rise and increased storm surges. So they've reinforced the coast by building a very robust wall in front of the site to try and protect it. But another important consideration is that bare stone is generally not meant to be bare. In most structures, not brochs, it's meant to be covered by a protective surface finish, which shields it from the elements such as rainfall. So this is an example of a site. This is Tamra Moore Herring Station on Tamra Moore off the west coast of Scotland. In areas where surface finish is still present, the sandstone is intact. Areas where the surface finish has been lost, the sandstone has undergone significant decay. So it stands to reason that buildings that were once covered with surface finish, but now aren't due to abandonment or active removal of a finish, are now weathering extensively due to water ingress. So a sensible solution is to reapply the surface finish and actually recoup the authenticity of the site. Managed loss approach. Unpopular to a lot of people, but it's really preserving sites by record. We understand that in a climate change future, we will lose sites. The particularly vulnerable sites are coastal. But in this day and age, we can digitally document sites to fantastic detail, where you get things like 3D models, where you can interact with sites. So, of course, even if the site is no longer there, you still know as much about it as possible, and you can interact with it even virtually. I'll talk through what climate change really is, what underpins it, what we've experienced, and what we will experience in the future. Introduced some climate data and showed how it can be integrated with archaeology and heritage science, and some action that's been taken on significant sites. So I'm almost finished. So I'm going to go through a very brief, but I think quite amazing case study at Upper Glendevon Reservoir. I'm not sure if some of you might have seen this on Twitter, but it really showcases the warmer, drier summers climate change future in Scotland. So this is Upper Glendevon Reservoir. It's in central Scotland. It lies at the headwater of the River Devon in the Ochil Hills, and is the first of a series of 3 reservoirs built in the 1950s. So alongside that, here's some climate data. So we have particularly focus on June, July, August, where rainfall was significantly lower than the monthly mean. So what does this look like? Well, here's a GPS map of the route that I went a few weeks ago on a walk. So you walk past the lower Glendevon Reservoir and up to the upper Glendevon Reservoir, where it looks as if I've walked right into the middle of the reservoir. And I did, because the water level is normally at 140 feet, but when I visited, it was 72 feet below normal. And you can see the sheer lack of water behind the dam wall. It's reduced to a puddle in comparison to normal levels. The soil and sediment beneath have cracked like somewhere in the south of Spain, not central Scotland in September. But what does that have to do with archaeology? Well, at roughly 90 feet is the old valley farmhouse that was flooded in the 50s to make way for the reservoir. The locals have said that on occasion the chimney stacks have become visible, and only in 1976 and 2003 has the site been completely exposed. And you can see it here. You've got the farmhouse and the field system and a small trickle of water running past it, which would normally be completely engulfed all the way up to the tree line that you can see on the side of the catchment. So this is the old boundary walls, the old farm boundary walls, and the building itself is fantastic, and we believe actually a first in the UK. It was one of my research colleagues, Tim Meek, said that it was conserved as drowned. The building shows clear signs of surface finish and was harled on the sides and the rear, and sneck harled and ruled at the front. But it's not just the farmhouse. In 2003, when the site was exposed, there was a paper produced of local findings, and they included a rare burial monuments, a round cairn, possibly a square cairn. And ironically, it's only through climate change that we've actually been able to see these sites. So warmer, drier summers seen in action. And I think this is a fascinating site that I kind of had to discuss. It's a clear visualization of warmer, drier summers. So do keep an eye on rainfall next summer, because if it does become visible again, it is well worth a visit. So to summarize, our climate has changed markedly in the last 60 years, exposing us to warmer, wetter winters and warmer, drier summers. Archaeology and heritage sites are being exposed to more extreme climatic conditions, having a potentially destructive but relatively unknown impact on the built environment in Scotland. So a more nuanced approach is needed to safeguard important sites in a climate change future. including my research and the research of others. For example, using Borwick as an example, it serves as a first attempt in the literature to try and integrate complex weathering processes with real climate projections and real building stone. So when you look closely at our historic environment, you can begin to see how it is influenced by climate change, which I believe could be the overarching influence on the longevity of Scotland's most treasured archaeology and heritage sites. So I hope you enjoy my talk. Thank you for listening, and I'd be happy to hear any questions.